let's pull that up real quick. Anytime.
Some of these like harder than what you would like the last page.
Some of them could have, depending on how well you're able to interpret the picture that you get on your calculator, some of them could have been more or less challenging than others. Okay, we did the first one together though, right? Okay. All right, for number 2, what did you get for part A? Good. Okay. The rational roots theorem. We should have gotten plus or minus 1, 3, 7, 9, 21, 63, and oh, hold on a second while my computer decides to stop responding. Anytime, OneNote. Should have also gotten all of those numbers over 2, and then all of those numbers over 4 as well. I don't know why this is, there we go. Why am I getting these also over 2 and over 4? Yeah, because those are also the factors of 4, right? Okay. Then it's calculator time. Of course, anytime if you can't see, please just stand up and turn off the lights. Oftentimes, second hour the lights are still on because first hour it's often too dark in the room with the lights off. But this is pretty decent. So we'll go ahead and start by trying to look at the graph. So I typed it in and graph from negative 63 to positive 63. And I see some stuff happen, but it all happened quite close to the x-axis, right? So I'm going to zoom in here to take a closer look. So this is negative 60, so that's like negative 30, negative 15. I don't know, negative 7 or so. Looks like I'll capture everything I'm interested in. So I'll do that. That's just a guess. Again, you could have picked other things. Okay, so this is the picture that I get, and I'm concerned with these x-intercepts. So looks like we have like negative, well, that's not quite negative 3, right? You see how it's passing through before negative 3? So maybe negative 2.9 or something. And then that one looks like definitely right in the middle, negative 1.5. And then looks like positive 2.9 over there also. Okay. So now I'm going to compare these numbers that I got off my calculator to my list. I don't see negative 2.9 or positive 2.9 anything close to that on my list other than positive and negative 3, which it's definitely not positive and negative 3. So these ones are probably irrational. Negative 1.5 is on my list. Or positive, yeah, negative 1.5 is on my list right at negative 3/2. Using my bend, bounce, or straight theorem, determine the number of times this could occur. So this one is a straight, so it can be used only once. The same thing with positive 1 or 2.9. Negative 1.5 is a bend, so that could be used, I'm sorry, it's not a bend, that's a bounce. And since I have 4 maximum, it could really be used 2 times or 4 times, right? But can it be really used 4 times? So I have 1 and 1, and then 4 more would make 6, and that's too many. Kate, what's your question?
I just don't think I would do it.
Okay, when you say that, what is that?
The straight and the bounce.
So I'm looking at the picture, and I'm looking at each one of these x-intercepts and how the x-intercept is going through or is passing through the x-axis.
Oh, okay.
So like 2.9, it goes straight through, right? Negative 2.9, it goes straight through. At negative 1.5, it bounces. So that's how I'm getting the straights and bounces.
Yeah.
Straight means it's used 1 time. Always 1 time.
Okay.
Bounce, it's going to be used an even number of times, at least 2. So it could be used 2 times, 4 times, 6 times, etc. But we're capped at 4 total solutions.
Okay.
So if these are used 1 each, it has to just be used twice. Chloe.
For D, if you don't have like, or C, if you don't have like a number and it's negative, is D just none? Or is that not how it
So
How'd you get it?
I looked at negative 2.9 and looked to see if it was on the list in part B.
Okay,
Because it's nowhere on the list, then it's probably irrational.
okay.
And similarly with positive 2.9, right? The closest thing to that on the list is positive and negative 3, but I looked at the graph and it's definitely not going through at exactly positive or negative 3. So I'm pretty sure that those are going to be irrationals. So my table, negative 1.5. I put both of my irrational things together. I have imaginary things, and then I have my total. The total is 4, always from the fundamental theorem of algebra. I have 2 irrational solutions, and I have negative 1.5 can be used twice. That leaves me no room for imaginary things. So I have really just 1 set of possibilities. It's this. So when I start my synthetic division, I have only 1 candidate to use. That's negative 1.5. Everybody okay there? So that worked, right? So that's good. And I could try to factor this by grouping here. It looks like it would work, but I'm just going to do 1 more synthetic division because I know I can use negative 1.5 2 times. So that works. So because negative 1.5 gives me a remainder 0, I have x plus 1.5. And because it gives me a remainder 0 second time, I have another x plus 1.5. And then my leftovers are 4x squared minus 28. And now this looks a little weird here because I have decimals inside of my factors, and usually that hasn't happened, right? But if I look at this factor, I notice there's a greatest common factor there, right? There's a number that goes inside of both 4 and 28. That number would be 4, right? So if I factor off that 4, I'd have x squared minus 7. And 4 is really the same thing as 2 times 2. Everybody agree with that? So I can multiply one of those 2's into there and one of those 2's into there. And that'll clean up those weird looking factors so that everything has integers now. Because it's kind of weird to say, okay, here's this polynomial that has all integer coefficients. Here's its factored form that has decimals in it. That's kind of weird. Should have all the factors should be integers, coefficients. And all we had to do was a little bit of rearranging to get that. And now that we're in factored form, to solve this, we can just set each of these pieces equal to 0 and solve. So here I get negative 3 over 2. Here I get negative 3 over 2. Here I add 7 to both sides and then square root. So I get plus or minus, and then the square root of 7. So those are my 4 solutions. So that bend, bounce, straight theorem was important in that it helped know that we had to use that negative 1.5 a second time doing the synthetic division. And the irrational conjugates theorem was important because it helped us pick out that negative 2.9 was irrational, so we shouldn't be trying to use that to do the synthetic division. And just FYI, the square root of 7 is negative, or is 2.6-ish. So that's really what that number was, 2.64, yada, yada, yada. All right, let's go on to the next one then. What's our answer for part A? 6. What's our answer for part B? Everybody agree with that? Well, 12 is a factor of 12. The constant term is 12. So now let's type this in and make sure we can see our picture. I would also say to you guys that being able to get the picture out of your calculator is like a pretty gosh darn important part of being able to do these problems. If you can't get these things typed into your calculator and manipulate your calculator to get a decent picture out of these things, that's a problem. So make sure that you're spending some time playing around with your calculator and figuring out how to do this. If you're getting errors and things, come talk to me and we'll sort that out. And I'll take a look at what's going on and give you some feedback as to like why you're getting errors on your calculator when you're trying to do this. but you definitely need to be able to use your calculator to get a decent picture. So I typed in my polynomial, and I set my window to -12 and +12. Those are the biggest and smallest numbers from my list that I just wrote down there. And I'm going to hit graph. Okay. So it looks like I have something at -1 and +2. I'm going to zoom in a little bit closer there, just so I can get a little bit better picture of what's going on. Because I wasn't quite sure if those were touching or not from the previous picture. By taking a little bit closer look, I can see they definitely are touching. So I have two x-intercepts. I have an x-intercept at -1 and an x-intercept at +2. If to do part D, are there any irrational solutions here? No, right? I see both of those on my list, so there's nothing going on weird there. So if I use my bend bounce straight theorem, what kind of intersection are these? Are these bends, bounces, or straights? These are both bounces, right? Okay. So how many times could a bounce be used? Not once. 2, 4, 6, 8, etc. So an even number of times. What's the maximum that it could go to, though? 6, okay. Now, can we really get 6 out of these, though? No, why not? Because there's 2 of them, right? So one of them has to be at least 2, the other has to be at least 2. So we can't get a 6 out of either one of these. All right, so let's make our table then. So I'm going to write in both of my x-intercepts, spot for my irrational stuff, a spot for my imaginary, and a spot for the totals. Okay. So -1 could be used twice. +2 could be used twice. We know there's no irrationals, and the total's 6. So where do the other 2 solutions have to be? They'd have to be imaginary. Caden? Yep. So there's more than one possible solution set going on here. So you're absolutely right. So this one could be 2. This one could be 4. That leaves zeros for everything else. And this one could be 4. This one could be 2, leaving us zeros for everything else. They can't both be 4 because you only have 6 solutions. So this is it. We don't know which one of these 3 situations we're going to be in, but we're going to have one of these 3 situations. Is that okay? Okay, so you're dead on that we don't know it's going to be 2 and 2, but I have to run through all 3 possibilities. So there is a possibility of us finding an imaginary solution in this problem. We don't know if we're going to have that yet, but it could happen. So this is how we can finally tell if whether I should be looking for an imaginary solution or not, because we can't see those when we look at the graph. But if I build out this table of possible solution sets, I'll get some clue as to whether it's even possible. All right, so let's start our synthetic division. I'm going to start with -1. Now we have to be a little bit careful when we're starting this setup. Notice that we have no x to the 4ths. So got to make sure that we have a 0 there. How many of you guys tried doing this and forgot the 0? I'm guessing more than one of us. Harley? Oh, thank you. That would have made life pretty difficult. So I have a 0 and then a -2. And then -5, 12, and 12. Thank you. All right. So now let's rock and roll here. So -1 again, because I know it works twice. So why bother changing? I don't know. I'm not going to. Worked again. Now, it's possible -1 works again, but I don't know it's going to, so I'm going to switch to 2, because I know 2 is going to work twice. Worked again. At this point, you could try factoring by grouping. If I look at that, that will work, grouping, but let's just do one more synthetic division, because I know 2 is going to work another time. So if I do this, let's say I get -1 gives me a 0 remainder, so I know x plus 1 is a factor, and it happens twice. 2 gives me a remainder 0, so I -2, x minus 2 is a factor, and that happens twice. And then I have this stuff left over, which is not factorable, so I know I'm done. This is my factored form. It turns out that we were in the first of those 3 possible solution sets, the one with the 2 imaginary solutions. That's what's happening here. So the last part then, if I set each of these equal to 0, and solve, I get -1. I get +2. And then when I subtract 3 from both sides, and then I square root both sides, and then because I'm square rooting a negative, I get my I. So there's my 2 imaginaries there at the end with plus or minus I root 3. Is this feeling any better here as we go through things? So the place where probably all of us could spend to use a little bit more time is looking at the picture and kind of seeing what other information we can tease out of that thing other than just the x-intercepts, right? I spend as much time looking at the picture as I probably did doing the synthetic division. Because once I've spent enough time looking at the picture, I have a pretty good idea of how the synthetic division is going to work. And I don't have to spend much, if something goes wrong there, it probably won't. Because I've already kind of figured out how it's going to work. I just have to kind of confirm it. So really, when you're doing these, you can't spend too much time looking at the graph and thinking about all the little theorems and whatnot that you can kind of tease some information out with. We spend as much time not factoring with the synthetic division as we do factoring. All right. Is this the last one then? Yeah, okay. For what?
For the X.
I mean, I'm happy to repeat what it is. What do you need?
I just think like the G
The factored form?
Yeah.
So you have x plus 1 and then the squared after it. You have x minus 2 and then the squared after it. And then you have x squared plus 3. You're welcome. Yeah. Yeah. Okay. All right. Should we talk about 4 then, Caden? plus or minus, you have the positive and the negative, right? Remember, the plus and minus is always count as two things because you have the positive and then you also have the negative. We just conveniently write it with the plus minus symbol just so we don't have to write it lots of times, but they do count as two of them. Yep, good question. All right, number 4, part A. How many solutions? Okay. Oh yeah, Mr. Kulik, why you're so mean? What's our list? Plus or minus 1, 2, not 3. 4 of those should work, right? 5 won't work. 6 won't work because 3 didn't work. 7 obviously doesn't work. Right? Oh, 7 does work. Oh my goodness. So 8 should work. Does not 9 can't work because 3 didn't. 10 that can't work because it doesn't end in 0. 12 works. Yep. No, 12 doesn't work. You lied to me. 13 won't. 14 should though. 28, 32, and then 56. Oops, forgot my plus or minus there. And then 112, and then 224, I think. I think I got them all. It's like the Pokemons, you got to catch them all. All right, I got that thing already typed in there. I did that while we were finishing up writing down the things for the previous problem. So I'll graph this from negative 224 to positive 224. Now I know I'm going to have to zoom in a lot. Like it's kind of silly to do this much because I'm quite certain there's no zeros way the heck out here. But got to check. And the calculator is done doing stuff. I didn't even see anything happen. So that tells me everything is really, really close. So if this is like negative 200, it's like negative 100, negative 50, negative 25, negative 10. That probably seems good. Maybe I'll just go down to like negative 10 and positive 10. Take a quick peek here. If I have to zoom again, I might have to zoom again. Yeah, I'm going to want to zoom again there. That's some confusing stuff going on right there that I want to get a better look at. But it looks like if I go between negative 4 and positive 4, I'll get everything that I need. Yeah, I'm glad I looked again. Okay. So, let's see. This is negative 1. That's negative 2. That's negative 3. So maybe that's negative 2.5. And then I have negative 2 and then positive 2.5. Are any of these irrational or likely to be irrational? Yeah, the decimal ones are. Because if I look at my list up here, I have no fractions up here at all. So the ones that I can see that are clearly decimal, I know are going to be irrational. Everybody good with that? Okay. So the bend, bounce, straight. Well, these two guys are definitely straights, so they're only used one time. What about negative 2? What is that? Yeah, that guy's a bend. So how many times can it be used? Odd number, 3 or more, so 3 for sure. 5. Can we use 7 though? No, because we already have 2 accounted for up here. So, and we only have 7 total. So 5 is the most we could do. All right. So we'll do the same thing here. We'll make our table. Okay, our total is 7. We know we have 2 irrationals. If I have 3 times the x minus, or if I have 3x minus 2's, that gives me 5 total. I need to get to 7, so 2 more would have to be imaginary. The other possibility is I have 5 negative 2's, have to have 2 irrationals, have to have 7 total, leaving me no room for imaginary. So this one, it is possible I have imaginary solutions in here. It's possible. I don't know that for sure, but it could happen here. Everybody okay there? Okay. Let's set up our synthetic division. I know negative 2 is what I'm going to use because it's the only rational. And then, thankfully, I don't have any skips there. Oops. So that worked. And I know I can use this 3 times, so I'm just going to do it again. Um, 56. Worked again. And I know I can use it one more time. So let's do it again. Oops. So that worked. Now let's look at what we have, because we don't know if we can use this 2 more times or if this is as many times as we can use it, right? Negative 2 could either be used 3 times or 5 times. Before we try this again and maybe have it not work, let's look at what we have left. So negative 2 gives me a remainder 0 3 times. So I have the factor x plus 2 3 times. And then I also have this. Notice that that's in the quadratic form, right? I have something to the 4th, something to the 2nd, and then a constant term. So I should be able to factor that using my factoring tree methods. So let's try to do that. So I need something that multiplies to give me negative 28 and adds to give me negative 3. What are those 2 numbers? Multiplies to negative 28, adds to give me negative 3. Should be able to do this. Negative 7 and positive 4, right? And because that middle variable is an x squared, I know in the factored forms they're going to be x squareds. So it turns out, because we didn't have any more x plus 2's there, that we were in that first situation where we have some of everything. We have some real, some irrationals, and some imaginaries. So if I set each of these factors then equal to 0, I get x equals negative 2 3 times. x squared minus 7 equal to 0. If I add 7 to both sides and then square root, I get plus or minus the square root of 7. Then x squared plus 4 equal to 0. If I subtract the 4 and then square root both sides, and then because I'm square rooting a negative there, I need to use an I. And the square root of 4 is just 2. So I have plus or minus 2i. So those are my 7 solutions then. So kind of the nastiest part about this one was you had this piece left over at the end that still could be factored more, but you couldn't use synthetic division to do it. You had to factor this using the factoring tree because its factors have no rational factor, no rational solutions in them, right? They're all imaginary or irrational things. So there is a possibility still in doing these problems you have to use those factoring tree techniques from last semester. Okay. Do we feel a bit better about doing this process? Well, good, because you're going to get some more practice today. So if you're still not feeling great, you're still going to get some more practice here today. So, with this, I'd like you to work with somebody else. So, find another person that you'd like to work with. One of you should definitely have a functioning graphing calculator. I'd like you guys to do as much as you can in class here today. Whatever you don't finish is fine. Do as much as you can, though. 1 sheet of paper per group is fine. Please put both names on the sheet of paper. Okay? Do as much as you can, but whatever you finish is what you're turning in. So yes, that means it's due at the end of the hour.